Okay, who's excited? Wait, let's do this the right way. Pull your clickers out. You can get points for answering dumb questions. That's what I'm going to do today. You guys deserve points just for being here. Okay, you guys can log in. Polling's open. Hit A if you're excited. It's the last day of school or classes. Hit some other letter if you're not. A if you're excited. I won't start counting yet because anybody still need to log in? It always takes longer the first time. Yeah, I thought about making a long string of questions for you. We could get lots of clicker points for way of review. But I decided we can cover more ground, which I think you'd be happy if I don't take all the time for that. Anyway, I'll be asking you stuff and telling you stuff. 10, 9, 8, 7, 6, 5, 4, 3. Well, what were all you guys people doing? 3, 2, 1. Okay. Okay, one person's not excited. Okay. All right. Now be honest. Polling open. Hit A if you're sad it's the last day of this class. I won't get offended. Is anybody sad this is the last day of class? Hit A if you are. Anything else if you're not. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Hey, 89% of you. Well, thank you. Okay, I've prepared 3 ways. We could either just randomly take your questions. I've gone through my notes. But there's no way, we can get through all this. But I can just head through that as we think of things. And I finished the final last night. So I can be looking at it too. I figure it'll be some mishmash between the 3. But if this isn't heading the way you want, this is your review. Raise your hand. Let me know. Logistics. I have your papers back. They're sorted semi-alphabetically by sections of the alphabet, so you can get those after class. I've also posted the your grade on WebAssign, but the paper's there. Your final, okay, when's the final? Thursday. Next Thursday, right. Where? Here. Right here. When? 10:30, right. Same rules apply. You can have a calculator. You can have your cheat sheet. It's same format, same types of questions. I get them from the same place. I ended up with 60 questions before you spaz. Almost everybody tends to finish 30 in 50 minutes. You get 2 hours for this one. But also that way each one is worth less points, so you don't have to stress as much about each individual one. That was my rationale for that. The only difference with the final, of course, is you don't get to retake it, because there's no time.
One question.
Yeah.
We can study the previous exams, right? The 6 exams that we've taken to help us with the final?
Can you study the previous 6 exams? I hope you do. That's why they've been up there, and why I write solutions and answers, yes. That and the homework. Yes?
So we don't have a study guide?
Nope. In my mind, the study guides are the homework, the exams, your book. They got big, full, bold-faced sections. There's key words. The end of the chapter mentions it. You've been taking notes all along. I've never been a big fan of just handing you like, yeah, here's every single thing we covered. Good luck. I felt it. So no, I don't have a study guide that I'm actually passing out to you. I do have these things. I know you're like, so what? That 10 minutes tell your story. Remember, the library can video you for free if you want to like document your experience here at the U. I'll put those out again. Yes?
Was there one question on the exam that you took off?
Is there one question?
Yeah, it said maximum 29. Maybe I read it wrong.
No, that's good to check. If well, I'll check it later. Not waste time. No, it was supposed to be 30, so I could have done a typo or something went funky. It was supposed to be out of 30, so I apologize for that. I will double check that. Okay. Raise your hand if you think of something. Well, first we did About Science, Chapter 1. And so, yes, I'm asking at least one question about the difference between a fact, a theory, a hypothesis, a law, or a principle. So it'd be helpful if you knew the differences. I remember some questions early on. In science, a fact, a lot of people think that's rigid, unchanging. That's the way it is forever, which is not true. Facts can change. It's a close agreement between people, observations of natural laws. And it tends to work that way. Welcome, Rachel. That's what they call a fact. But, 300 years later, they might realize, we've learned more stuff and it's a little different. So it can change. Perfect example is the world is flat. A law or principle. I don't know, before that one. Hypothesis. Who remembers what a hypothesis is?
An educated guess.
That's exactly what I'd say. An educated guess. Based on what you know, you'd predict. Based on some of these facts you might have, you go, well, I'm going to predict this will happen. A law or a principle is kind of like a general hypothesis. We've been gathering all these facts, but we make this hypothesis, and it always seems to work. It's been proven over and over again. Doesn't mean it can't change later. Like Newton's laws. They seem to work for us, and they've been working for a long time, so that's why we call them a law. So what's a theory? Anybody remember? Most correct answer we have so far. Yeah, it's very similar because I thought that's what a fact was. I thought that's what a law was. It's kind of like facts are like smaller, and laws are.
Educated guess is what again?
I'm sorry, what?
An educated guess is what?
Hypothesis. Thank you. Well, here I wrote scientific theory, a synthesis of a large body of information that encompasses well-tested and verified hypotheses about aspects of the natural world. So in my mind, the theory is kind of the biggest. It incorporates laws and facts, like general relativity. Brian, you like that one. That it's a theory to explain all this stuff based on certain laws and facts. So it's a synthesis. Well, that kind of sums up chapter 1. Any questions there? All right, chapter 2, we got into 2, 3, 4, and 5, covered Newton's laws in motion. So who remembers which one's Newton? I know you know this one, because I think most of the superhero papers were on Newton's laws. So which one's the first law? An object in motion tends to stay in motion, or an object at rest tends to stay at rest, unless acted upon by a force. Right. Very good. So inertia. This has inertia. It doesn't want to move. The only way to get it to move is Newton's second law, right? Apply a force to it. Hey, I moved it. And Newton's second law We learned that that motion you gave it was proportional to the force you push on it. You push harder, it has a greater change in its motion. But if it's bigger and has more inertia, more resistance to change of motion, it won't go as fast. So big objects don't accelerate as much for the same force. It always seems kind of weird to me. I hope it does to you too. You know, when we were there, you know, we spent a lecture or two on this, and it's, what, huh? See, feel better. Doesn't it seem a little simpler now? Oh yeah. Okay. I hope so. Galileo figured this all out. Oh, yep. We had net forces. Remember, you can have more than one force acting on something at a time. But it's that net force, the combination of all of them acting together, that determines whether this thing changes its motion or not. Example. I push on that box with a force. What other force is acting on it? The table, a normal force. Friction. Back. Anything else? Gravity. The earth pulls it down. Well, weight. Anything else? Supporting force, we call the normal. That's the table pushing back up on it, perpendicular to the surface. See why we called the in optics the normal? They're both anyway. I guess if you're getting technical, there could be air resistance when you're going against it. What's that? There is a buoyant force. Good job. And which direction is that? Up. Well, why does it have a buoyant force? What principle is that called? Another scientist's name. Okay, forget the name at the moment.
Everything has buoyancy.
Everything has buoyancy?
Is it Bernoulli's principle?
Oh, it's a good term. Bernoulli's principle? No. Archimedes. Archimedes' principle. And he said, for what Brian's getting at, there is an upward buoyant force on objects equal to the weight of the fluid they displace. So if this block takes up so much space, it displaces so much air, which is a fluid, remember, air is a fluid because it flows. So it displaces a certain amount of air. If you weigh that air, that's equal to the buoyant force. It's like you in a swimming pool. You jump in the pool, you displace a certain amount of water. The weight of that water equals the buoyant force. That's Archimedes' principle. It allows things to float and sink. Remember, if this is at the bottom of the ocean, does it still have a buoyant force? Yeah, it's still displacing fluid, but why is it not floating? Well, if this is sitting on the bottom, what's that tell us? Why is it not floating? Say that again.
It weighs more than it
Right. If its weight down is greater than the buoyant force up in the ocean, well then yeah, do you see that the net result will be down? It sinks. What's it tell us about the density of it?
So,
Oh, hold on.
it needs to be equal.
Say again.
To float, it needs to be equal. The weight and the buoyancy need to be equal to have it float.
If these two are equal, it won't go anywhere. Because the net force is 0. So it'll stay wherever it's at. That's neutrally buoyant, like a fish. If you take on more air, like a submarine or a fish, then this becomes bigger, and then you'll rise up to the top. Once you get to the top, some of it sticks out. Is it displacing more or less water? Less. So what happens to the buoyant force? Yeah, it goes down because you're displacing less water. So there's less buoyant force, and they become equal again. And it stays put at the top. Let's all do this combination of forces. So back to this one. Vertically, is it moving? Are these boxes moving? No. So that tells us that the buoyant force and the normal force must add up to the same value as the guy's weight, the object's weight. They're balanced. The net force is 0. And if the net force is 0, what's the acceleration? 0. You can have forces acting on something and it not change its motion. Yep.
So if you have a wrecking ball on a table, so it can go down because there wouldn't be enough support?
If you have a wrecking ball on a table, yes, if the weight is greater than the support force, then yes, it'll break through the table.
It would bow or break.
Yeah. So horizontally, we have two-dimensional motion. We are balancing the pushing force and the frictional force. If those are equal, what's the block doing? Very good. It's either staying at rest or moving at a constant what? Velocity. Both of those cases, it's not changing its motion. Things at rest like to stay at rest, or things in motion want to stay at motion at a constant velocity. There's no acceleration, because if these are equal, the push and the friction, the net force is 0. The net acceleration's 0. The thing is not changing its velocity. It's staying put or maintaining whatever it was at. It's just like brushing cobwebs off from way back when. Okay. Oh. Yeah. No, we did that. So hopefully it seems obvious now that acceleration is a change in motion, change in velocity. So I'll write it down again. We also had, and we've used a lot in different forms, or you can think of it as distance equals velocity times time. Remember, if you're going so many meters per second for so many seconds, that'll tell you how many meters you're going to get. Or think of velocity as a change in position with time as you change your location. Remember this formula, distance equals rate times time, worked with waves too. The speed is still distance over time. The distance is the wavelength. The frequency gives you the time. Remember, frequency is 1 over the period. So they're really the same formula, just applied to different waves or objects. Free fall, we did that. You'll probably notice I spend a little more time at the beginning stuff because it's more rusty. than the stuff we just did. In free fall, that's where you're just under gravity. And what's the acceleration of gravity? Good. 9.8 meters per second squared. Or if you only needed approximately 10. You know, if you're doing it in your head. So, what does that mean? If you drop something, what does 10 meters per second squared mean?
That means it's acceleration over time.
That's its acceleration. And acceleration is the change in velocity. So how much is it changing its velocity every second? 10 meters per second. You remember that? See, if you start here at the top and you drop it after the first second, how fast will it be going? 10 meters per second. Because it just changed its velocity by 10 meters a second every second. So how much will it change the second? It'll be at 20 meters per second, and 30, and 40, and so on. Because it's changing its velocity. What happens to the distance? I drew it roughly to scale. It doesn't change linearly the same amount each time. See, the velocity did 10, 10, 10, but the distance gets bigger and bigger. Because we had, like the height it falls, the distance was 1/2 the acceleration. And there's that squared factor. So the distance keeps getting farther and farther. We did that with the carts too, where I let a cart move along. And if it's accelerating, it's covering more and more distance each second because it's going faster and faster. Okay. What can I throw up? This. What's the acceleration on this rod when I throw it in the air? It's 9.8. In which direction? Towards the ground. Is it always that?
Yes.
How about when this stops at the top? What's its velocity at the top? Right there. Its velocity is 0. What's its acceleration? 9.8. Good. See, you got that one now. Two-dimensional motion. What if I throw it in an arc like this? Well, you treat the vertical the same. It went up, it went down. But now you have a horizontal component, right? What happens to the horizontal speed after it leaves my hand? In its flight, how does its horizontal velocity change? It doesn't. Very good. Why? Who said that? Because there's no what? There's no net work on it. There's no net force pushing on it. There's no net acceleration. So we go back to Newton's first law, and inertia just keeps it going horizontally. But meanwhile, the vertical velocity decreases, gets to 0, and then increases in the other direction because it's being accelerated. Do you remember that? Remember the monkey chute? The cougar chute? We shot it out, and it went while the cougar fell. So this one had no horizontal velocity, the cougar. But the bullet did. And that got it from over here on the left to over here on the right. At the same time, it was accelerating down. So they fell together like this. Tell me when you're ready, Brian, so you can watch also. Dum, 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 dum. And they hit each other.
So what about terminal velocity?
That's what I was going to do.
Things that fall will eventually reach terminal velocity or a constant velocity at some point.
Right, terminal velocity. So we got weight down, and you have air resistance up, right? Or some people call it drag. It's the same game again of balancing forces. When these two become equal, does it accelerate? No. So as something starts to fall, what's its acceleration? 9.8. As it falls, what happens to that? Acceleration. It decreases until it gets to 0 if the thing reaches terminal velocity before it goes splat. So the faster and faster the object falls, the greater the air resistance until it doesn't accelerate anymore. It stays at that speed the rest of the fall. How do you find weight? How do you find your weight? What'd you do? That's right. It's Newton's second law. But the acceleration for our weight is due to gravity, so throw in. And now you know your weight. Does that change on the moon? The weight, sorry. Yes, because you have a different acceleration due to gravity. Does your mass change on the moon? No, you're still the same. Would it be just as hard to push you on the moon horizontally? Yes, because you have the same mass and the same inertia. So it would take the same force to change your motion. Because you have the same mass, inertia. Okay, that was redundant. Newton's third law. We had fun with that one. What is it? Yeah, opposite, equal and opposite reaction. Or some of you remember action and reaction. For every action there's an equal but opposite reaction. And my becoming new favorite way to say it is all forces come in pairs on different objects. If I push on you, you push on me. If the earth pulls down on me, I pull on the earth. You just flip the roles. And the force is always the same. So, when I get mad at him, which I don't, and I whack him in the face, psh, the force of my fist on his cheek is the same force as his cheek back on my fist. Even if his head goes flying backwards, which it probably wouldn't because I would hurt my fist. But the force is the same. When you get in a collision, and it's a big semi-truck, and little Timmy on his tricycle, unfortunately we know who's going to win. But the force on Timmy is the same force back on the semi. So why does Timmy lose?
Because the mass of the semi is much greater as compared to
the mass. Back to the second law. Right. If the force is the same between the two, then the big mass has a little acceleration. And the little mass has a big acceleration. And the semi can only push on little Timmy as hard as Timmy can push back. Example, I push on the wall. Equal and opposite forces. If I could push harder than the wall could push back,
you'd be Superman.
then it'd be like the wrecking ball on the table. And my force would be stronger than the support force, and I could knock the wall down. But the force between the two is still the same. It's just the wall can only push so hard. So that's all the harder I need to push to get through. Let's do a demo. I think this one kind of reviewed quite a bit. Oh, before that, little Timmy and the truck, that's right. How could little Timmy win that collision?
If it was over a longer period of time.
If it was over a longer period of time, you're getting there.
More distance?
More distance, longer period of time. Good, good. What term is this referring to? Involves where you extend the force over a longer period of time? Momentum and impulse. If little Timmy were traveling at the speed of light and the Mack truck is going 1 mile an hour,
Oh, Timmy would win.
well, he'd at least do better. The point is, he'd have a lot more momentum, because momentum is mass times velocity. So he might have a little mass, but if you get a lot of velocity, you can have a lot of momentum. They're both going to come to a stop, so there's a change in momentum. And what caused that? A force over a certain amount of time. And that's where, yeah, you can change this time to affect the force you feel. So why do you guys wear helmets?
More time between your head and what's hitting you.
Yeah, if your head crashes on the ground, it's the same change in momentum whether you're going to wear a helmet or not, right? You're going yay fast, and you stop. Same change. Well, if you can extend the time of the collision by some padding, you need less force to do that. Remember, you want to go thud if you fall out of a building. Don't bounce. Okay. Who's going to win? We'll give you another point. I'm going to roll the balls at the same time down those. Who do you think will win? Polling's open. A, the high road. B, low road. This is the high road. See, it's higher. This is the low road. I'm going to let go of them at the same time. Who will get to the end first? Go. This involves a lot of concepts of motion. What's that?
The same mass.
I can't hear you. Yeah, it's still the same if you haven't logged in yet or logged out.
Does the marble go the same mass?
These are the same. Yes, the balls. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, you guys are pretty much split, but more of you think the low road, slightly. Okay, let's just do it. Drum roll, please. The low road wins. So let's discuss why briefly. Philosophically, maybe you shouldn't always take the high road, right? They start at the same height, so they have the same what energy? Potential energy, which is due to gravity. They get down to this height. What?
Well, it should double, one is going to double because you're going farther down. So for B. So because on the low road, you're going to have more acceleration on the low road, or option B, because there are two changes in potential energy. And then you only have one going up because you have enough kinetic energy to make it back up the ramp.
And that's my point. Very good. I'll repeat that now. From here, the top, to here, they have the same speed because they've had the same change in energy, potential energy into kinetic energy. So they have the same speed and energy. But at this point, this one drops some more. More potential energy changes into kinetic energy. So this one's now moving faster. He's accelerated more than this one. So at this point, the low road ball has a greater velocity. Do you see that? So the low road gets ahead of the high road. But Here, the low road has to come back up, and it has to slow down and convert some of that kinetic energy back into potential. So now it's going slower than it was down here. How do you think its speed up here now compares to the speed this one's been going? Yeah, it's now matching, but it's already ahead, so it wins. Let's do it again. And this time, watch. When the low road gets up to here, try to visually compare the two's velocity. Yeah, I can start it later too, that'll help. So conservation of energy, potential and kinetic, affects the speed. And one more time, because this is fun. Potential energy was mass times gravity times height. If I had changed the height of which? High or low?
Well, for both of them.
If I change the height of both, we can just do it. I'll start up higher, right?
No, I mean the tracks.
Raise it up?
Raise,
What do you think will happen?
more acceleration, of course. but
More acceleration,
it's
true.
going to be faster still.
But the low road will still be faster? Correct. Same reasonings. Good. Newton's laws, momentums, impulse, collisions, energy. Look at that. Two-dimensional motion. Buoyancy, Archimedes principle. Do you know what density is? Very good. Density is mass over volume. So another thing, if an object sinks, what's that tell? I think I asked this, but I can't remember if I finished it. What's that tell us about the object's density? Very good. It's more dense than the fluid that it's in. If it floats, it's less dense than the fluid it's in. Good. Atmospheric pressure. The air in the room has mass, and it exerts pressure down on us. You know, all the stuff above me pushes on me. And that was, pressure was proportional to density, gravity, and height. That's why we make water towers up tall and put the water up there. Because the pressure is greater at the bottom, all that water pushing on it. It can shoot it out faster with more pressure. But the air does the same thing. You get more air on top of you, height, you feel more pressure. And atmospheric pressure can do lots of things. We shot a ping pong ball through a pop can, remember that? Your ear still hurt? Straws. When you drink a straw, do you suck the water up? You're causing a change in pressure. If you lower the pressure in your mouth, the greater pressure from air pushes the fluid up the straw. How high do you want to push it? That depends on the difference in pressure. Okay, let's do this one. We got about 9 minutes left. That's probably just enough time to have this chaos ensue. And honestly, it'll probably be fastest, and then I'll answer your question. If you just come down and grab one, they're different colored pipes. Grab one pipe for you, except for purple and black. We're not going to use those. Don't grab purple or black. Grab one pipe, go back and sit down. We'll do a little demo and end. come grab those. What's your question? Excellent. Pressure is based on depth, not how wide the container is, how much you have. Very good. Don't need those. So, oh yes.
Is the final pretty evenly dispersed in the sections, would you say, or not?
Yes.
Lean towards the beginning?
No, the final, I went through a lot last night. They're fairly balanced, yes. If anything, I probably unintentionally asked slightly more questions about what we discussed today, motions and laws and forces, but because it kind of applies to everything we did with the forces in motion. So, but I still, it does cover the whole gambit, slightly more the motion forces stuff. But there's just as many sound questions, and there's still quite a few optics questions. There's still heat transfer questions.
What's the answer to the last question?
The answer to the last question? I don't remember off the top of my head. Okay, these I call palm pipes. And I cut them to different lengths. You play them like this. This was the intended. That's why I call them a palm pipe. You can do a flute too. But we're doing this. Well, whoops. Didn't need that. I'm going to conduct you guys. When I hold up the white origami cup, everybody with a white pipe will play their note once. When I hold up, and this is supposed to be orange, so get this in your head. This is orange, this is yellow. When I hold up an orange, then everybody with orange plays once. I did a scale, so we got the notes for a standard American chromatic,
For an actual, like, do, re, mi, fa, sol.
do, re, mi, fa, sol.
Diatonic.
Diatonic, thank you, thank you. So let's just go for it and see what happens. I have faith in you, so I chose a Mozart piece. I really did. Okay, let's practice.
That was bad.
This one's red? Okay. Here we go.
So just once?
Yeah, when I hold it up, tap once. If I hold it up a second time, you can tap the second time. As our music majors, or people know, Mozart really did write that when he was a kid. It's the music to Twinkle, Twinkle, Little Star, or ABCs, or Baa Baa Black Sheep. He called it Vous direz-je, Mama, but he's French. But anyway. Some quick lessons with that, and then I'll stop. I'll have you come down and put them in here, and you can grab your papers. But they're different lengths because you drive the frequency, right? This is the vibration. You're pushing the air around. This wants to resonate at certain frequencies. The length determines the wavelength. The wave will the wave will propagate down. It'll reflect off the end and come back on itself. All the waves do that. Then they interfere and superimpose. The one that fits, that matches crests coming the two ways, constructively interferes and resonates. And that sets up this wave. This is a longer wave. This is a shorter wave. So it's vibrating faster and has a higher pitch. And notice the color scheme I used here. Rainbow. Which color has longer wavelengths? Red. So I made the red side longer. And purple shorter. So there's your quick review of waves. All right, it's been a pleasure. Thank you very much. If you'll return your pipes on your way out, I'd appreciate it.
What time is the final on Thursday?
10:30.